Welcome to 17th lecture of analog microelectronic circuits, and in today's class we will continue our discussion on MOSFET based amplifiers. So in the previous classes we have looked at common source amplifier and also common source amplifier with the source degeneration. So today we will look at the other two configurations quickly. So what we will see today is we'll try to derive the expressions for input impedance, output impedance, and voltage gain. That will be our aim for both common gate and common drain amplifier. So probably at this time you may be wondering, you are seeing different circuits every day, but that should not give you any sort of confusion. Let me start the circuit diagram of a common gate amplifier. So only one thing we know, that for a common gate amplifier, gate should be kept common. Right, gate should be kept common for input signal and output signal. That means your gate terminal will be common when you look at the amplifier circuit from the small signal perspective, right? So why I am making that point here is, so gate terminal is common for input and output voltages. So why I am making this point here is, directly by with the understanding if the gate terminal is common, we cannot directly ground it, right? So gate will be common, gate will be ground, gate will be act as a reference when it will act as a reference only for your inputs and outputs. Otherwise, we have to provide a DC voltage to the gate. I hope that is clear, because unless and until we give a DC voltage or the other conditions for the transistor should be satisfied, your VGS should be greater than VT and your VDS should be greater than or equal to VGS minus VT. These DC conditions should be satisfied in order to operate the transistor in saturation, right? So this is very important. That means we have to bias the gate voltage. We will actually connect a DC voltage to the gate. Right. Now, where will we apply signal? We will apply signal to the source. So we'll apply signal to the source. This I'll mark it as V in, and I'll take output from drain. So from drain, I'm taking output V out. So for that purpose, I'll actually use a resistance here at drain, and I'll mark it as RD, and this I'll mark it as VDD. So you should understand that this VDD and V bias both are DC voltages, right? But for small signal, now when you consider the signal voltages, so the purpose of the voltages here, the purpose of this voltage VB, 1 second. Yeah, the purpose of this voltage VB here and this VDD, both these voltages will establish the DC conditions, right? That means this V bias will actually give a gate voltage with respect to, yeah, so source there is no other DC, so it will definitely the V bias will be the VGS voltage, and VDD through RD will establish a drain voltage to the drain. That means the DC conditions are or will be always satisfied. Now, since we know about that DC conditions, I'll be taking you to the small. So I'll just draw the small signal picture of this circuit. The small signal picture will be something like this. Gate will be shorted to ground, and here you will have signal V in. Here at drain you have a resistance that is connected to VDD, but now that VDD also will act as a ground, because when you consider small signals or when you consider the small signal picture, no need to consider the constant voltages. That is why we shorted V bias to ground and VDD also to ground. So this is the picture now. This is the small signal picture, or for this circuit we are going to draw the equivalent circuit, right? So how will I draw equivalent? First I'll keep the equivalent of MOSFET. So the equivalent of MOSFET is, these are the three terminals. This is gate, so plus minus VGS. We will have the current GM VGS flowing in this direction. I will not consider lambda initially. We will deal without lambda. Now for this, I have to add the additional components. That means at source, I have to connect V in. Gate is grounded. Drain, I have the resistance RD, which is connected to ground. And this point is the output voltage, right? Are you guys with me? Can I get some response in the chat box? All right. So I hope all 51 are with me now. So, but if you have any doubt in between, it can be something what I repeated in the previous amplifier configurations also. But please don't mind. You can ask doubts in between also. Right. So this is the equivalent small signal picture. So can I ask this question? How many of you have still doubt why I am making this VDD and V bias to ground in the small signal picture? How many of you have still that doubt? You can unmute and ask now itself. Anyone need more clarity on that? Okay, so if you have doubt, please please ask. Please don't hesitate to ask that. All right, so this is a small signal picture. Now what is our aim? Our aim is actually to find voltage gain, input impedance and output impedance. So for that, first I can write what is V out. What is V out? How can I write V out? Can I get response from someone? Maunika, can I get the response from you? What is V out in this case? You can unmute. Maunika is not there. Okay. Joel, are you there?
Yes, sir.
Yes, Joel. Joel, can you tell me what is V out?
Sir.
Yeah, I'll help you, Joel. No problem. If you are making mistake, also it is fine. I can help you. You have a doubt?
No, sir, no doubts.
Okay. Okay, Monica. Yeah, all right. Probably it is a network issue. Right, right. Joel, can you unmute for some time?
Yes,
Yes,
sir.
yes. Uh, I think. Okay. So now tell me what is V out? What will be V out here? V out will
Oh,
be the voltage across RD, right?
yes, sir.
Now, what is voltage across RD?
Oh,
What is the current flowing through RD? This is the current.
GMVGS, sir.
Right. So what will be V out?
GMVGS into RD.
Very good, very good. So so with a minus sign.
Yeah, sir, minus n.
Okay. Yeah, you can mute, John. Thank you. So it is minus GM VGS into RD. Right. Now, what is VGS? So our aim is to get voltage gain. Voltage gain is V out by V in. So now to get that, I should replace this VGS also with V in. But if you look at the circuit diagram, you will understand that V in is measured from this node, the source node to ground. VGS is measured from gate or from ground to source node. So directly you can say that VGS is equal to minus V in, or if you have doubt, you can in fact you can actually write a KVL here. So what will be the KVL? You can write it. So from ground to source, that is minus VGS minus V in equal to 0. You can apply a KVL here. You can write the voltages from starting from, you can consider the loop from ground to source, and then you can write it as minus VGS minus V in equal to 0. That means your VGS is equal to minus V in. So if I substitute that back here, I can write V out as V out is equal to GM into V in into RD, or voltage gain AV equals V out by V in equals GM into RD. Now, one thing you can note, the voltage gain of common gate and common source are almost same. The only difference is in the polarity. So in the common source amplifier, we have seen that voltage gain is minus GM into RD. In common gate, it is GM into RD. The difference is because, see, probably you would have observed that in common source, we are applying the signal to gate and keeping source as common. Now we are applying signal to source and keeping gate as common. That is only difference. As far as DC is considered, now in common gate you have a DC voltage to the gate. Even in common source also you have the same thing. But the difference is in where you are actually connecting your input voltage. That is why you are getting a positive. So your common source gain is inverting, but your common gate gain is non-inverting. That is a difference, right? So looking further, probably you can answer this also. What will be Rin in this case? Can anyone tell me what is Rin? Whether Rin is infinity in this case, Rin. Rn is infinity. Yes, Akram, Rn will be infinity only if you are looking at gate, right? But now, where is your signal connected? Signal is connected to source. Now, the input is this. So you are looking, whatever source you are connecting, that source is connected to source, the source terminal of the MOSFET, and the input impedance is the impedance seen at the input terminal. Now the input terminal is source. So that is not infinity. We have to find what is the input resistance. It is not infinity. We have to find it, right? If your input is given to gate, then it will be definitely infinity. Now, what about R out? So R in, we will find it separately. What about R out? Output impedance. Lambda is anyway considered as 0. So there is no small r naught. Then what will be R out? Any answers? RD, yes, correct. So R out is RD. So there is no difference in the output impedance compared to your common source amplifier because it is same. Now let us find what is Rin in this case. So the input impedance of a common gate amplifier. Let us find that. Rin. So in order to find Rin, I am taking the same small signal equivalent circuit. Sorry. Yeah, the same small signal equivalent circuit I'll take. Let me redraw that equivalent circuit again here. This terminal is grounded. Probably I'll mark with, this is VGS. This is GM-VGS. And here you have RD resistance. Yes, Maheshwari, I saw your response. Pradyumna, I have seen your response, RD. Now we need to find Rin, input impedance. So how will you find input impedance? The same way we will try. We will connect a test voltage to the input terminal. We call this as V test. And we will mark this as I test. Right. And whatever is V test by I test, that will be your Rin. So Rin here will be equal to V test by I test. Right. Now, how will you find this? The very first thing is I'll try to find a equation for I test. What is I test here? I test is a current flowing in this direction, but we know that the current flowing in the opposite direction is GM-VGS. So I can write I test is equal to minus GM into VGS. That is the first step. Now the second step is the relationship between VGS and V test. The same as before. If you write a KVL here, or you can see that VGS is the voltage from ground to source, but V test is the voltage from source to ground. That means both are related as with the negative sign. So V test is equal to minus VGS. So I believe I'll be substituting this VGS over there as I test equal to GM into V test, or I'll get V test by I test as 1 by GM. So this is Rin. 1 by GM, which is Rin. Right. So now we have obtained the voltage gain of a common gate amplifier. Voltage gain is GM into RD. Now input impedance is 1 by GM. Output impedance R out is equal to RD. So this is the case when your lambda is equal to 0. Now we will find out with lambda not equal to 0. But one thing to note here is your Rin is very small compared to the previous cases. So what is the previous case? Both in common source and common source with degeneration, your input impedance was infinity, but here your input impedance is 1 by GM. So why am I calling this 1 by GM as very small? So in most of the cases, the value of GM, the GM values are, say for example, it will be in the range of milliamps per volt, 1 milliamps per volt, or even lesser than that. A maximum, say up to 5 milli or 10 milli is the maximum value. So that again depends on the you know that GM is nothing but you can write in different forms, mu and Cox W by L into VGS minus VT. So all this depends on the overdrive voltage, the mu and Cox value and the aspect ratio. But in most cases, it will be GM will be in terms of milli. For that reason, 1 by GM is considered as very small, right? So this is all about lambda equal to 0, and this is again common gate. Now let us continue this. So if you have doubts, please ask. Let us continue for the for lambda not equal to 0 case. Before that, let me have a small comparison between CG and CS. So in both cases, CG voltage gain is here GM into RD, but there it was minus GM into RD. Now input impedance, here it is 1 by GM, there it was infinity. Output impedance, it is RD in both cases, right? In both cases it is RD, and this is the case when your lambda is equal to 0. So if you have any doubts, you can unmute and please check with me now. Otherwise, we will go ahead and find the CG amplifier, the same derivations with lambda not equal to 0. All right. So I believe that it's clear. Or can I get response from one or two guys? Abhirami?
Yes, sir.
Abhiram, yeah. Thank you, Akram, for the response. Abhirami, is that clear?
Yes, sir, clear.
Okay. Okay. All right. Mohan?
Yes, sir, it is clear.
Okay. Nitin? Nitin is not there. Okay. Namit?
Yes, sir.
All right. Okay. Thank you. So now what I'll do is I'll go ahead and I'll draw the equivalent circuit for CG amplifier with lambda not equal to 0, and I'll try to get the same expressions. Same in the sense I'll try to derive the expressions for common source, voltage gain, input impedance and output impedance. So again I'm going for the equivalent circuit. So it is plus minus VGS. Here we have this GM VGS component and R naught across the this one. Now this is drain, this is source, and this is gate. Right. This is the equivalent equivalent of the MOSFET. Now we have to modify this. So how will I modify? I'll modify this accordingly by connecting V in here, this terminal to be grounded, and to this terminal I need to attach the RD resistance, which is to be connected to ground, and this is V out. This is the equivalent circuit, right? But the same way what we have done for the previous we will do here. You have a current source in parallel with a resistance. I'll just modify this here itself, and I will draw it as yeah. So that modification I'll use a different color so that you will also identify that something is done here. So GM VGS R naught, and this R naught is in series, right? I hope it is clear, the changes what I have made here. Now I will go ahead and write the same thing the same way. So the first expression what I'll write is Vin is equal to minus VGS by observation and by the previous analysis, that is clear. Now how will I write V out? V out can be written as, so the current what we have assumed is current is flowing in this direction. So V out can be written as minus I into RD. Now I should write what is this I, right? So what is this I? I can be written as V in minus GM VGS into R naught divided by yeah. So probably I can explain that. So how is this I? So I is the current here. So previously in the case of common source with degen, if you remember, you had a resistance here as Rs. So in that case, we wrote the current as the voltage, the single voltage source divided by the sum of the resistances. The three resistance were there. But now it is not the case. You can try in different ways. So let me write an expression for that. Current is flowing in this direction. I into Rd right. So minus I into Rd minus I into R naught plus Gm Vgs R naught minus Vin is equal to 0. I wrote a KVL. I just applied a KVL here, and from this I will write the expression for I. So what is I? So one more thing I can do here, I can write Vgs also in terms of Vin. So I'll write it as minus IRD minus IR naught minus Gm into R naught into Vin minus Vin equal to 0, right? Or I can write here as I into Rd plus R naught. I'll take to the other side, that is equal to minus of Vin into 1 plus Gm R naught, right? So I have written in this form. So or I can write I as minus of Vin into 1 plus Gm R naught divided by R naught plus R. So don't worry, this is the first time you are seeing an analysis in this form. So it will take some time for you to get familiar to this. So don't worry for this, right? So it is minus Vin into 1 plus Gm R naught divided by R naught plus Rd, right? So this is the expression for I. Now if I is known, you can directly write V out. What is V out? V out is minus I into Rd, so minus will get cancelled. So it is Vin into 1 plus Gm R naught divided by R naught plus Rd into Rd. Or voltage gain can be written as V out by V in equal to 1 plus Gm R naught into Rd divided by R naught plus Rd. This is the voltage gain expression. Is this clear? Any doubts? So this is AV. Right. Now, can I get a response whether this derivation part is clear? All right. So, but if you have doubts, please ask. But one more thing I just want to clarify or to write here is, can you tell me what is Rin in this case? The previous case we obtained Rin as 1 by Gm. Now what is Rin? Can anyone of you unmute and tell me what is Rin? Anyone?
Sir, R not parallel RD, sir.
Rin, what you're telling is R out. Rin is the resistance seen from this side, right? At the source. There R0 and RD are not in parallel. R0 plus 1 by Gm, Pradyumna. Okay, R0 plus 1 by Gm. Okay, so you have taken in this form. Previously it was 1 by Gm and now it is in series with R0. Is that you meant? Okay, so there is a small variation. It was 1 by Gm is correct in the if it is lambda is not equal to 0. So tell me, how will you find that? How will you find input impedance? So how did we find input impedance in the previous case? In the previous case, we applied a voltage, test voltage here, and we wrote what is V test by I test. The same way we can follow here as well. So what we will do, assume that in place of V in you have applied a V test and the current is I test, and current is in this direction. Right now the current is in this direction. Now when you evaluate V test by I test, it will be same as this. It will be same as this. The only difference is in place of minus I, you will have plus I test, or you can, in fact, you can use the same expression. in place of I, you will have minus I test, and that minus and minus will get cancelled. So you can directly write what is V in R in as V test by I test from the expression what we already obtained. No need to derive one more time. That will be equal to R naught plus RD divided by 1 plus GM R naught. How many of you understood what I explained now? Because input impedance, how will you find? We similarly, how you find output impedance? In a similar way, you can connect a test voltage to the node or the terminal which you want to find input impedance and mark it as V test and I test, and then find what is V test by I test. So use the same loop. So use the same equation. Only thing is, instead of minus I, you have plus I test, because I was actually flowing in this direction, but I test is in the opposite direction. Right. So if you replace that in this, definitely you will get you will end up with the same answer, R in as R naught plus RD divided by 1 plus GM R naught. That is R in. Now to write R out will be same. While finding R out, I think there is no doubt in R out calculation, because R out will be same as before. You have RD and R naught, both will be in parallel. So it will be R naught parallel to RD. Yeah, RD parallel to R naught. Yes, very good. Right. So that is all about common gate amplifier. So yeah, now see, this is a third amplifier configuration we are studying right now. There will be a tendency to think that, okay, this is difficult, or there are a lot of things to remember. So I'll tell you the trick how to remember these things. So once I finish the next configuration, common drain amplifier, all right, Akram, you want me to explain Rn again? Yes, I'll do that. So what I was telling is, yeah. So what I was telling is, you can in place of this, write this as V test and take this current as I test. Right. Now the current is actually flowing in this direction, I test. Now write the same equation. So I'll do that here. I'm considering this loop, this entire loop, to evaluate what is V test by I test. So I'll just rewrite this. So how will I do? I will take this as V test plus V test minus GM VGS into R naught minus I test into R naught minus I test into RD equal to 0. I test is flowing in this direction. That means we will actually consider drop as plus minus and plus minus in this way. Right. Now in this you can substitute VGS as minus V in. So this will be plus V in R naught. That's all. Take I test to the other side and write what is, sorry. This is V test. V in is V test now, right? Yeah. So Akram, is that clear? Now from this you will end up with the same relation here. So minus will not be there. Let me write it here itself. So V test into 1 plus GM R naught is equal to I test into R naught plus RD, or Rn is V test by I test, that is equal to R naught plus RD divided by 1 plus GM R naught. Is that clear? Akram, can I get a response from you? All right. Okay. So so no need to look at this side. So I have just this is again Rn calculation I have done. All right. So if this is clear, if you have no doubts, I'll just quickly go through the next amplifier configuration and wind up the theory part, and we can start with the numericals from next day. Meanwhile, if you have doubts, please ask. So this is the last type of amplifier, CD, common drain amplifier. So to quickly look at the circuit diagram, as we discussed before, drain will be common. So again, drain common doesn't mean that drain can be grounded directly. It should be connected to some DC voltage. Input will be given to gate and output will be taken from source. So we have to connect a resistance here RS, and this will be V out. This will be the simple common drain amplifier, right? Now for the small signal picture, we will replace this, or we will draw the same amplifier as, yeah, that I think by this time you people know that for small signal picture, this has to be grounded for small signals. Right. So let me quickly derive the expressions for voltage, gain, and other things. So let me draw the equivalent of MOSFET first. So plus minus VGS, and this is GM VGS. This is source, drain, and gate. Now to gate, I have to connect input voltage V in. Drain should be common, connected to ground. At source, I have to connect the resistance RS, and this node is V out. All right. I hope all 51 are following. Right. Now, first let us consider the case of lambda equal to 0. So when lambda is equal to 0, let me write what is V out by V in. So what is V out in this case? What is V out? Can anyone unmute and tell me what is V out? Jayaditya? What is V out in this case?
Hello.
Yes, go ahead, Jayaditya. Yes.
Yes. It's GM, BGS, and RS.
Yeah, GM BGS into RS. Very good. Thank you, Jayaditya. Now, what is VGS? Yeah, Maheshwari. Yes, I got it. I saw your answer. GM VGS RS. What is VGS? Can I get some response? What is VGS? Praveen, what is VGS? Kiran. Oh, Kiran, your response is VGS is V in. Okay. Any other answers? Praveen, are you there?
Yes, sir.
Yes. Praveen, can you tell me what is VGS? Praveen, you can unmute.
V in, sir.
Oh, V in. Okay. Okay, you can mute. I'll explain. V in minus V. All right. Yeah. So to find VGS, previously in all the previous cases, in your common gate case or even in the previous cases, this did not come actually. So you may be confused. So how you can get the relationship between VGS and V in is just write a KVL there. So it is V in. So from ground to this point is V in minus VGS. Then here is plus minus V out. So minus V out is equal to 0. Or I can write VGS as V in minus V out. Right. So if you look at this equivalent circuit, we can see that VGS is between this V in and V out. Right. So from the KVL, I will get that VGS is V in minus V out. Or I can write V in as VGS plus V out. Right. So that is a relation. So with that, if I write V out, what is V out? V out can be written as GM RS into VGS will be replaced as V in minus V out. And from this, I can write V out is equal to GM RS into V in minus GM RS into V out. Or if we take V out to the left side, I'll get V out by V in as GM RS divided by 1 plus GM RS. That is the V out expression. Sorry, voltage gain expression. GMRS divided by 1 plus GMR. Yes, Kirtana, I saw your response. GMRS, Jessica, Kirtana, Abhirami, Manikandan, Mohan. Yeah, I'm just seeing your responses. Yeah. So V out by V in is this. Is there a doubt here? So this is AV, this is voltage gain. So one more thing I can comment here. You have seen a similar kind of gain expression for your common source with degeneration, but then there your expression was GMRD by 1 plus GMRS when your lambda was equal to 0. This is CS with degen, right? And this we approximated to RD by RS by considering GMRS as large. So similar way, if you do an approximation here, if GMRS is greater than 1, the voltage gain of this will be close to 1, right? Because if you neglect the 1 in the denominator, GMRS by GMRS will be 1 itself, right? It is 1. So even though we call it as common drain amplifier, as far as voltage is considered, the gain what is given by this amplifier circuit is 1 itself. But there are many uses for this CD configuration also. We will look at some of the uses later. Now the takeaway from here is you can get a maximum voltage gain of 1, right? When you consider GMR greater than 1. Otherwise your gain will be lesser than 1 only. It will be very close to 1. Usual case it will be 0.9 and 0.98. In that way you will get a gain, right? So that is all about gain. Now what about input impedance? Input impedance is directly infinity because you are providing input to gate. What about output impedance? Any idea about output impedance? Manikandan, can you help me in finding output impedance?
Sir, is it RS?
Okay, so this point, whatever resistance you are seeing should be the output impedance. Now it is RS from here to here, but if you look up, you will get some more impedance, right?
Excuse me, sir.
Okay, from the V out. So
Yeah. So yes, 1 second, Manikandan, I think. Yeah, Praveen. Yes, Praveen.
Sir, why Rin is equal to infinity, sir?
Okay, Rn, where am I connecting input? Input is connected to gate, right?
Yes, sir.
So there is no gate current. So when you find V by I here, it will be equal to infinity because of zero current.
Okay, okay, sir.
Okay, yeah. Yes, Manikandan, go ahead.
sir, is it 1 by GM or
It is 1 by GM parallel to RS.
parallel
Very
to
good.
RS?
Yes, very good. Yes. Mohan, I saw your response. Madhusudan, I have seen your response. It is 1 by GM parallel to RS. So others who are wondering, I'll explain how it is. R out is R out I'm finding for lambda equal to 0 case. So I'm just drawing the equivalent circuit. Let me draw this. VGS. This is GM VGS. This is ground, and this is the point. So here you have already RS resistance. Now I am asking you to find what is output impedance. So how will I do? I have to connect a test voltage here, right? Test voltage I have to connect here, V test, and this current is I test. But for at that time, what I will do, I will actually place this RS apart, and I will find V test by I test, and their final output impedance will be equal to RS parallel to the impedance what I am getting from V test by I test, right? This is what we explained before. Now I will take the same way. So what is V test by I test? How can I write this? So if I want to write this, I will first write what is VGS. What is VGS? VGS is equal to minus V test. That is clear. Now what is I test? I test is current flowing in this direction, but the current flowing in the other direction is GM VGS. So it is minus GM into VGS. Now if I write VGS over there, it is GM into V test, or your V test by I test is equal to 1 by GM. V test by I test is 1 by GM. Right. So what is your final R out? R out is RS parallel to 1 by GM. Right. Yeah. So that is R out calculation for lambda equal to 0. Now okay, so now let me take you to one more thing. So can you tell me what will be lambda, what will be your R out when lambda is not equal to 0? R out calculation when lambda is not equal to 0. Can anyone tell me what will be R out? Any answers? Okay, so the difference is when your R out, when your lambda is not equal to 0, the difference is you will have one more resistance here as R naught. Right. Very good, Kartikeya, Maheshwari. Yes, it is RS parallel 1 by GM parallel to R1 because you have R naught in parallel. R naught is connected from this point to ground. We already have RS here. That is also from same point to ground. That means this RS and R naught are in parallel. Right. So what I can do is I can write the already existing impedance as RS parallel to R naught and the remaining thing parallel to this thing. That means all these three impedances will come in parallel. Is that clear? So again I am repeating, it will take some time for you guys because this is the first time you are doing a small signal analysis. So you have to understand what is this DC analysis and the related stuff what we have done before, and then now for the past 3 classes we are doing small signal analysis. So it should be very clear for you guys. Right, so you can repeat and you can just redo this again and you can make sure that you are clear with this. So if you conclude here with the common drain, so I haven't done one case. The cases for your common drain with your lambda not equal to 0, I did not find I did not calculate the output sorry, the voltage gain, but we know that it will be maximum will be up to 1. So even if you consider R naught for the calculation, it will not affect the voltage gain much. Your gain will be very close to 1. It will not be more than 1. That is why I am not exclusively calculating that. So to conclude, I can write voltage gain of this will be very close to 1. Voltage gain I can say it will be close to 1, very close to 1. Then R in input impedance, I can write input impedance as infinity, and output impedance will be 1 by GM parallel to R naught parallel to RS, or I can say this is very low. Output impedance is very low. Right. So before taking any questions, I will just go for a summary here, a summary chart where we can just summarize all the amplifiers. And after that, I will take questions. So let me write the type of amplifier. So we have common source. We have common source with degen. We have a common gate. Final one is common drain. That is the first one. Then we will write the voltage gain. AV. So when you write voltage gain AV, there will be two cases, right? One with lambda and one without lambda. Let me write for common source without lambda first. It is minus GM into RD, or if it is with lambda, it is minus GM into R naught parallel RD. That is for common source. Now what is for common source with degen? It is minus GM RD divided by 1 plus GM RS, right? Or with the lambda, you have to bring in R naught also. So the numerator remains same, minus GM RD divided by 1 plus GM RS plus RD plus RS divided by R0. This is easy to remember because when your lambda is equal to 0, your R0 will be infinity and this term will vanish. So the expression will remain same. Now for your common gate, regular expression is without lambda it is GMRD. With the lambda, the expression is slightly modified as 1 plus GMR0 into RD divided by R0 plus RD. Right. So here also you can actually take R0 common outside. If you take R0 and cancel it, it will end up with GMRD itself. And finally, for CD amplifier, it is GMRS divided by 1 plus GMRS, that is without lambda. So with the lambda we did not do. If lambda we are considering, this R0 will come in parallel to RS only. So I can write it as GM into RS parallel R0 divided by 1 plus GM into RS parallel R0. That we haven't done, but I hope it is clear for you people. Right. So that is a voltage gain. So let me write the other expressions also. Let me use a different color. Okay, now I'll write input impedance here Rin. So Rin is very simple to remember. Common source in both cases it is infinity only because we are feeding to gate. Common source of the region also it is infinity. Common drain also it is infinity. Only you need to remember about common gate. Without lambda it is 1 by Gm, and with the lambda it is Rd plus R0 divided by 1 plus Gm R0. So this equation also will reduce to 1 by Gm. How? If you take R0 common and cancel, you will get only 1 by Gm, right? Because if you take R0 and cancel, it will be 1 plus Rd by R0 and 1 by R0 plus Gm. So when you put your lambda 0, your R0 will be infinity and it will be only 1 by Gm. So that is all about Rin. Now finally, let me write what is R out here for all the three cases. So R out is, the first is common source amplifier. R out will be Rd without lambda. With the lambda it is R0 parallel to Rd, right? So the same will be for common gate also. So that will directly write here. It is Rd here and R0 parallel to Rd, right? So when you compare common source and common gate, output impedances are same. Output impedance remains same. Gain also without lambda, gain also remains same, but only with a negative sign with a polarity difference. But input impedance there is a difference because the point where you are feeding input is different in both the cases. Now for common source region, I think this also you can remember. Without lambda, it is Rd. But with the lambda, the expression what we have found separately, R0 plus Rs plus Gm R0 into Rs, the whole thing in parallel to Rd, right? And finally for common drain, it is 1 by Gm parallel to Rs. If without lambda, if with the lambda, it is 1 by Gm parallel to R0 parallel to Rs. So this is actually the summary of all the four amplifiers. Now I can take questions. Before that, let me okay, I should have used different colors for lambda, right? Lambda 0 and lambda not equal to 0. Okay, I think you can sort out that. The first what I have written is without lambda and the second quantity is with lambda. Now, so if you compare, if you look at the voltage gain of the four amplifiers, you can see that the voltage gain of this is the smallest. This is providing the lowest voltage gain. So AV is very close to 1 in this case. And you have common source and common gate also almost equal voltage gain without lambda. Now input impedance is very small for common gate. So that way you can actually have a comparison. Now output impedance is in fact very small for common drain. So output impedance is low here. Is low. Here in common gate, input impedance is low. So the other cases are, we can consider it as moderate output impedance, or input impedance is high for all the other cases, right? So this is the summary of all the amplifiers. So with that, the theoretical and the derivation part of unit 1 is done. So from next class onwards, we'll take up numericals. We'll solve different varieties of questions so that you will be prepared for your exam also. So now if you have any doubts, you can unmute and you can ask me.